welcome back to our machine design series. Today we are discussing joints, and specifically we're going to discuss fastener stiffness. So this will be one out of 3 videos discussing how to analyze joints. In this first one we're going to focus on the fasteners, then we'll get to the clamped parts, so the members that are being clamped together by the fastener, and lastly we'll talk about what happens when we apply an external load to a joint. So first, let's start off with a few basic definitions that we're going to need. So of course, remember that the purpose of a bolted joint is to clamp 2 or more parts together. So we're always going to be dealing with 2 or more members. And tightening a bolted joint by twisting the nut produces a clamping force, and we call that clamping force the pretension or the bolt preload. So we established that pretension is developed by twisting the nut in a bolted joint. In a joint that is held together with a screw, we get a similar preload or clamp load through the effective grip length of the screw. So let's take a second to define what we mean by grip length. We are going to use the variable L to denote the grip of a joint. And that grip length of any connection is the total length of the clamped material. So for a screw, there's going to be an effective grip length that is not exactly the full length of the screw. There's a nice chart in your textbook that walks you through how to calculate this grip length. But just know that theoretically it is the length of the total clamped material, and that includes washers. Okay, so to relate this pretension or bolt preload to an amount of stretch or deflection in the fastener, we're going to model a threaded fastener as a series of springs. Okay, so here's a drawing of the model we're creating here for our threaded fastener. So on the left, I have our base model of this bolted joint. So in blue, we've got a couple members that are being clamped together, and then in green is our threaded fastener, our bolt. You'll notice that there's a section of this bolt that is not threaded and a section that is threaded. There's also washers on the top and bottom, and we include the thickness of those washers in the overall grip length L for our bolt. The portion that is not threaded, so from where my cursor is now up to just underneath the head of the bolt, that is the length of the unthreaded portion of our fastener, or the length of the unthreaded portion of our grip. And the length of the threaded portion of our grip is going from where the threads start down to just underneath the nut. Okay, so we take this starting model and we're going to turn it into a series of 2 springs that represent this bolt. The top one is the stiffness of our unthreaded portion, and the bottom is the stiffness of the threaded portion. Because these 2 sections of the bolt have a different geometry, they're going to have different stiffnesses. And so we need to represent each of those separately, and then of course we know how to combine springs in series. We need to simply add together the inverse of each one and then take the inverse of that. We'll get to the math part of it in a second. But first, let's just talk about how we're going to use this stiffness to find the total extension of our bolt under a particular preload. So first we need to go back to the very beginning of this class and remember how to calculate the total extension of a uniform bar in pure tension. So I want you to go back in your notes and see if you can find an equation that relates total extension to force and geometry and material properties. Did you find it? It is delta, which represents our extension, equals the force times the length of the bar divided by E, our Young's modulus, times the cross-sectional area. That comes from chapter 4. It also comes from your deformable bodies or mechanics of materials class. Next, we're going to use Hooke's law for springs. You remember that one? Hooke's law tells us that the force is equal to the spring constant times the amount of extension, and using this equation we can find the effective spring rate, K, is equal to EA over L. This is just taking F over delta equals K. If I rearrange this equation to get F over delta, I find that that's equal to EA over L. Now, since a bolt, as we talked about, has typically a threaded and an unthreaded section, we're going to model it as two separate springs in series with two separate stiffnesses. So let's write those out. All right, so here are our two expressions for the stiffness of the threaded and unthreaded sections of the bolt. I've labeled each of the variables except for E, which is just the Young's modulus of the material. Note that the major diameter area is used for the unthreaded portion. So this is just the cross-sectional area of the unthreaded portion of the bolt. And then for the threaded portion, we have to use the tensile stress area, which we talked about in our introductory video on threaded fasteners. So you can go take a look at that if you want a refresher. Remember that for standard sizes bolts, you can look this up in a table in your textbook. I think it's table 8-1. And if you have a non-standard size bolt, there's an equation in that lecture that you can use to calculate what the tensile stress area actually is. All right, so with that, we have our two separate stiffnesses. Now we need to combine them to get the overall stiffness of the bolts. And I'm going to borrow our diagram up here just to show what we're doing. So we're taking this model that we have of two separate springs, and now we're just combining them so that we have a single spring here. And it's going to have an overall stiffness of KB, just the stiffness of the bolt. And remember, to combine springs in series, we take 1 over the effective stiffness equal to 1 over the stiffness of the unthreaded portion plus 1 over the stiffness of the threaded portion. Now, if I take this equation here and I substitute in the expressions from up here for KD and KT, then I can write that 1 over KB is equal to the length of the unthreaded portion of the grip divided by Young's modulus times the major diameter area plus the length of the threaded portion of the grip divided by Young's modulus and the tensile stress area. And then I can combine those denominators and flip everything over so that I get an equation for KB that I can solve for directly. It's equal to the major diameter area times the tensile stress area times Young's modulus over major diameter area times the length of the threaded portion plus the tensile stress area times the length of the unthreaded portion. And let's box that. That is the equation that we will use to find the estimated effective stiffness of a fastener. We did it. We got the estimated effective stiffness of a fastener. Remember that if you have a bolt that does not have an unthreaded portion, it's completely threaded, then you don't have to do this last step of combining the two separate stiffnesses. Your total stiffness is just going to be equal to KT. You don't have to worry about combining it with anything else. Remember also that if you have some sort of non-standard fastener where you have maybe different diameters on one side versus another, you can combine more than two springs in series using this same concept. We just continue to add 1 over K3, 1 over K4 until you've got all of your sections of the bolt accounted for. And then, of course, you'd have to modify this equation too. But this is a very versatile method. So it works for both standard and non-standard fasteners. And this estimated effective stiffness is going to be really important after we develop the effective stiffness of the members. We're going to be able to come up with something called the joint constant, and that's going to tell us how much of an external load gets taken up by a bolt versus how much of an external load gets taken up by the members. And therein lies the real power of a bolted joint and the reason that they are so widely used and provide such strong connections. So I hope you're excited to learn more about that. And that's going to wrap it up for this video. I hope that you found it useful, and I hope to see you in the next one.